Okay, let's get right into it. Welcome to the Ultimate Examiner's Playbook for mastering what is, honestly, one of the most notoriously misunderstood topics across the entire Cambridge Computer Science and Information Technology syllabus, the Sensors module. Today's explainer is all about exam strategy, but we're going to look at it through a very specific, almost magical lens. Think of top-tier exam technique as a kind of magic. Seriously, in the wizarding world, casting the exact right spell yields a specific, powerful result, right? Well, in the Cambridge examination room, whether you're sitting for the 9626 IT paper or you're dealing with those crucial foundational concepts in the 0417, 0478, 2210, or 9618 syllabus codes, your magic spells are your structural frameworks. Cast the right structural spell, and you literally guarantee maximum marks. Today, we are focusing all our energy on a very specific beast: humidity, pH, and gas sensors. And by gas sensors, I mean oxygen, carbon dioxide, carbon monoxide, and NOx. Examiners consistently, year after year, report that this exact area is an absolute minefield where candidates just bleed easy marks. So we're going to deconstruct the exact strategies, the precise frameworks, and the specific structural spells you need to cast to achieve absolute exam mastery.
So, why is this so difficult? Examiners constantly report that candidates seriously struggle to apply their knowledge of these sensors, your humidity, pH, oxygen, CO2, CO, and OX sensors, to new contexts. And today, we are going to fix that completely. Look, it's one thing to memorize that a pH sensor measures acidity or alkalinity. That's easy. It is an entirely different challenge when you open that exam paper and it presents you with a highly specific, totally unfamiliar scenario. Maybe it's an automated agricultural system monitoring soil degradation, or maybe it's a smart city infrastructure tracking NOx emissions in real time. When faced with these curveballs, what happens? Students freeze. They completely freeze up and fall back on writing out generic textbook definitions rather than actively applying their knowledge to the specific problem sitting right there on the page. The theoretical architecture of this module doesn't just rest on knowing what a sensor physically does. It requires understanding precise definitions, causal relationships, and most importantly, integration with other syllabus areas. You have to be able to dynamically link the hardware of the sensor to the software processing the data and the physical environment it's operating in. If you can't do that, you can't get the top marks.
Let's look at two classic student profiles to show you exactly what I mean. First, we have Alex. Now, Alex is a hard worker. Alex has spent hours and hours memorizing the textbook. But when faced with a complex question about a carbon monoxide sensor in a high-stakes industrial setting, Alex completely panics. The result? Alex just overloads the answer with raw, disjointed computer science facts. We're talking a massive, dense paragraph explaining the chemical properties of CO, how the sensor is physically wired, and basic data input concepts. But there is absolutely zero analysis of the actual industrial scenario. The examiner reads it, sighs, and reaches for the red pen, giving a low mark because the actual question wasn't answered. Then, on the other end of the spectrum, we have Sam. Sam thinks they know the answer, immediately rushes through reading the text, and completely misses the command word requirements. The question specifically asks to evaluate the use of an oxygen sensor, but Sam just describes it. Red marks again. Both Alex and Sam are leaving massive amounts of marks on the table. They lack the structural spell needed to channel their knowledge into points that actually score. To ensure your paper is covered in green check marks instead of red pen, our explainer today is structured into 4 critical chapters: the Sensor Exam Challenge, Core Theoretical Principles, Systematic Processing Methodology, and Critical Examiner Insights. Let's jump in.
Chapter 1, the Sensor Exam Challenge. Let's decode exactly what the examiners actually want from you.
You absolutely have to understand the rules of the game before you can win it. The examiner isn't just checking if you've memorized a list of vocabulary words. They really don't care about that. The Cambridge Assessment Framework demands logical, structured reasoning across 3 very specific cognitive domains, prioritizing analytical depth over superficial breadth. Let's break this down because it's a real game changer. First up, knowledge and understanding. This is just your base layer. This is simply knowing that a NOx sensor detects nitrogen oxides in vehicle emissions. But listen to me, that base layer will only get you so far. Next is application. This is where you actually apply that knowledge to the scenario. For instance, explaining exactly how the analog data from that NOx sensor is converted into digital data so the central computer can actually process it. But the real magic, where the absolute highest tier marks live, is in the third domain, analysis. This requires you to evaluate the evidence, identify limitations, and draw rock-solid evidence-based conclusions. It is all about analytical depth. An examiner would much rather see a deeply analyzed, thoughtful point about the latency and calibration issues of a CO2 sensor in a crowded room than a superficial list of 10 different sensors. Depth always beats breadth when you are hunting for those top marks.
To consistently hit those analysis marks, you need the ultimate structural spell. I call this the computer science success blueprint, and it relies heavily on the PL framework: point, evidence, explanation, link. When you get a massive 8-mark question on deploying humidity and pH sensors in a smart greenhouse, you absolutely cannot just write a messy, rambling block of text. You start with a crystal clear point. For example, the pH sensor will continuously monitor the acidity of the irrigation water. Boom, clear. Then you provide evidence from the actual scenario. As stated in the case study, the specific crop requires a pH between 6.0 and 6.5. Next is your explanation, where you bring in the tech. If the sensor detects a pH of 5.5, it sends an analog signal to the microprocessor, which converts it via an ADC, processes it against preset parameters, and triggers the actuator to release an alkaline solution. Finally, the link back to the big picture. Therefore, this automated feedback loop ensures optimal crop yield without the need for manual human intervention. That right there, that is a perfect, examiner-pleasing paragraph that guarantees maximum marks.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Chapter 2, Core Theoretical Principles. Let's see how we translate textbook theory into actual method marks. In the Cambridge marking scheme, particularly for those really complex problem-solving questions, you don't just get marks for magically arriving at the final correct answer. You are awarded method marks for showing a logical, structured, and repeatable process. Systematic processing within the sensors module follows a 5-step standardized sequence. You need to internalize this to ensure you extract data correctly. Step 1. Identify elements. You read the prompt and highlight the exact sensors required. Let's say it's an oxygen sensor and a CO sensor for an industrial boiler. Step 2. Apply principles. You actively recall how these specific sensors physically interact with an analog-to-digital converter and a microprocessor. Step 3. Execute analysis. You look at the data provided in the exam. Perhaps it's a complicated table of fluctuating CO levels, and you analyze the relationships. Step 4. Verify results. You check for reasonableness. Seriously, if your analysis suggests a pH level of 25, you know you've made a fatal mistake because the pH scale typically only runs from 0 to 14. Step 5. Present formats. You write down your final answer using appropriate terminology, clear headings, and strict presentation conventions. Memorize this sequence. Practice it until it's second nature. It will absolutely save you when the exam pressure hits and the clock is ticking down. Let's look at the transformation in action. Notice the huge difference here. A flawed answer completely relies on generic definitions, like simply stating a humidity sensor checks water in the air. I mean, it's true, but it's incredibly generic, and it's going to score a fraction of the available marks. But a winning answer? A winning answer uses the PEL framework and deeply contextualizes the data. It explains that the humidity sensor gathers analog data regarding the moisture levels specifically in the museum's artifact room. It mentions that this continuous data stream is passed through an analog-to-digital converter, so the microprocessor can actively compare the current humidity against a stored preset parameter of 45%. And if the reading exceeds this, the microprocessor sends a signal to activate the dehumidifier actuator. Do you see the difference in quality? Making those cross-topic connections, bringing in your ADCs, your microprocessors, and your actuators alongside the basic sensor knowledge is exactly what the principal examiner reports highlight as the secret to transforming those red marks into green check marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Chapter 3. Systematic Processing Methodology. It is time for our interactive workshop. Knowing the theory is only step 1. Executing it under intense time pressure is step 2. I want you to imagine you are sitting in that exam hall right now. You have exactly 60 seconds on the clock to scan a massive, complex sensor dataset, interpret the underlying relationships, and extract the core trend before the examiner's timer runs out. Think of a complex data table showing parts per million readings from a whole network of NOx sensors at a busy city intersection, tracking over a 24-hour period. You absolutely do not have the time to read every single number in that grid. You need to employ rapid data interpretation skills immediately. You scan for the peaks. Maybe you spot massive NOx spikes at 8 a.m. and 5 p.m. You immediately interpret the relationship. Those peaks perfectly correlate with rush hour traffic. Boom. From this rapid extraction, you can start drawing evidence-based conclusions for your answer. You must practice this rapid scanning technique. Do not get bogged down in the raw data. Look for the story the data is actually telling you. While you are analyzing that data, you need to keep this fundamental rule from the syllabus at the front of your mind. You must identify limitations, assumptions, and alternative interpretations to evaluate the overall quality of your evidence. This is the evaluate part of the deconstruct, solve, evaluate methodology, and it's where students lose points constantly. Let's say you are asked to evaluate the use of a CO2 sensor in a large office building to manage the ventilation system. A superficial, rushed answer just says it works well to keep the air fresh. No. A top-tier analytical answer actively points out the potential flaws. What if the sensor is installed too close to an open window? That is an environmental limitation that severely skews data quality. What about calibration? If that CO2 sensor isn't regularly calibrated by maintenance, it might suffer from baseline drift, providing totally inaccurate, skewed data to the central microprocessor. By intentionally identifying these limitations and alternative interpretations, you demonstrate to the examiner a profound, professional-level understanding of how these computer science systems actually operate in the messy real world.
All right, our final challenge here is speed writing a comparative analysis. This is a crucial examiner requirement. When evaluating sensors, you must be able to identify both similarities and differences. You have to use comparative connectives like whereas, conversely, similarly, and in contrast. Often, you'll be asked to compare two entirely different approaches or two different sensor setups. A massive trap, and I mean massive, that students fall into is only talking about what makes the sensors similar, or worse, just listing facts about both without actually comparing them at all. Listen to this perfect example. Both the oxygen sensor and the CO2 sensor provide continuous analog data streams to the microprocessor. However, whereas the oxygen sensor is critical for immediate life safety alarms in the laboratory, the CO2 sensor is primarily utilized for optimizing the long-term HVAC efficiency. See how that tightly connects the concepts while clearly delineating their very different real-world applications? You are drawing mature conclusions about the relative importance, which hits the absolute highest assessment objectives.
Chapter 4. Critical Examiner Insights. Let's look at exactly what the graders are saying behind closed doors.
I love the principal examiner reports because they act as literal cheat codes. They tell you exactly what the graders are frustrated by year after year. And the biggest frustration? Generic answers. A generic answer is a failing answer. If the exam scenario is about an automated fish tank, your entire answer must talk about fish, aquatic environments, water quality, and the highly specific pH levels required to keep that marine life alive. If you ignore the fish and write a brilliant, scientifically flawless paragraph about how pH sensors are used to monitor soil acidity on a farm, you will get 0 marks, literally 0, because you didn't answer the question asked. The examiner desperately wants to see that you can take your abstract theoretical knowledge and apply it practically to solve the specific, unique problem presented in that exact paper. Always, always link your knowledge back to the context. So to recap those reports, ensure you avoid the top 3 fatal mistakes: providing answers that are too vague, forgetting strict presentation conventions, and failing to contextualize the data. Mistake number 1, vague details. Do not just write, "The sensor sends data to the computer." That's primary school level. Say, "The gas sensor continuously outputs an analog voltage proportional to the CO concentration." Mistake number 2, poor formatting and terminology. The Cambridge syllabus demands professional level skills. This means using precise, industry-standard vocabulary. Never call it the computer brain. It is the microprocessor. Mistake number 3, ignoring the context, which we literally just discussed. If you can systematically eliminate just these 3 errors from your practice papers today, I promise you, your baseline score will jump dramatically. Let's lock in this final system, your ultimate success blueprint. It's 3 simple rules. First, decode the command word. Does the question say identify, describe, explain, or evaluate? Because each of those words requires a completely different level of depth and a different structure. Second, apply the Peel framework to ensure your answer is structured, logical, and deeply analytical. Point, evidence, explanation, link. Never forget it. Third, execute your time matrix. Listen, do not spend 15 minutes writing an essay on a 4-mark question about a basic humidity sensor, leaving you with absolutely no time for the massive 12-mark evaluation question at the very end of the paper. Calculate your time per mark at the start of the exam and stick to it ruthlessly. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. But before you go, just think about this. As our smart cities become fully automated, what actually happens when a single, poorly calibrated NOx sensor triggers a massive citywide infrastructure failure? The real test isn't just passing the paper, it's deeply understanding the systems that run our modern world. Keep practicing, and I'll see you in the next explainer.